Okay, welcome back to lecture number 2 of Design of Machine Elements and Systems in Agricultural and Biosystems Engineering. This is just a continuation of the previous topic on the very basic theoretical knowledge on machines and machinery. Now, again, the kinematics is founded on the basic knowledge on the theories of statics and dynamics. And in kinematics, consideration of rigid bodies is made, and since it's kinematics, there's movement, there's displacement, there's velocity and acceleration. Now, a body can undergo movement in many ways, and one of which is translation, and it's just given that the body is rigid, point A to point 2, point 2 of point A will be via a linear motion. The displacement is linear. As the velocity and acceleration, that would still depend given on scenarios. Now, there's also curvilinear translation, and we see that points A and point P also are both going through curvilinear movement at the same time, because again, it's a rigid body. Now, there's rotation about a fixed axis as shown, and these are the points are not labeled, but accordingly, the points should revolve about a fixed axis, and after at some point, they should be at the same distance from that fixed axis. Now, there's also general plane motion as shown, like that of movement of a wheel, and there's the motion about a fixed point, which is generic for tops, and then there's general motion, and that would mean another motion of a rigid body that's beyond this identified types of motions. General plane motion can be broken down into two, that's translation and rotation. It's important to take note of this fundamentals of kinematics, as this would be involved in the analytical solution of kinematics problems, the movement of machines. These are just shown to represent the types of motion, but in general, a wheel would not be part of a machine, unless it's driven by a shaft. A top is not a machine, but let's move forward to the kinematics synthesis and analysis, where we talk now of a 4-bar linkage, which is here identified by a frame, crank, rocker, and a link. This is a crank rocker mechanism, and what's important for in the kinematic synthesis is the identification or the determination of the position or displacement of the parts. Given this is still a rigid body, and to know also the velocity and then the acceleration. Okay, so this is the bar, the same bar that was shown a while ago, the crank rocker mechanism, and we have the crank selected, and this is the rocker, and we can show how this moves, if we try to rotate it, so we see the mechanism of how it rotates. The frame, the frame is fixed, and it's constrained to the rotation of to one motion, and likewise at this point. Now, the other parts, the crank, it should be providing the motion, should be the source of power. Again, it's important to know that there should be a power source, and we'll leave that much later at the end of the class. But here we want to show the movement of the different links, okay, from the crank, the link, okay, to the rocker, and then the frame. We were talking about the movement of the different links, and where I was saying about the constraints, okay, of certain um, linkages, okay, of some links and the linkages. For example, at this point, it's constrained to only rotation, while this one, okay, it moves and rotates, okay, along a plane, and then moves along X and Y as well. Now, this motion, okay, the mobility of a specific mechanism is identified, or yeah, it's identified by the degrees of freedom, which is just the number of the independent parameters to specify the position of a specific link, okay, with respect or relative to a frame, okay. Now, different joints would have different degrees of freedom depending on the how constrained that that joint is, okay. For a revolute, okay, you have okay, for a revolute, okay, you have one, okay, no, sorry, yeah, a revolute is just a pin, so there's 1 degree of freedom, and there's a computation to that, okay. That's 6 times the NL minus 1, okay, the quantity minus NC. NL is the total number of links, while NC is the total number of constraints, okay. There's a better formula that involves the joints, and that would be, okay, the DOF, okay, the degrees of freedom, is equal to the 6 times NL minus NJ, and we have 1 minus, okay, the quantity minus the summation of the f of I, okay, from I1 to n sub j, and n sub j is just, okay, the joints with individual connectivity f of I. We see here that the n of c is actually okay, n of c is actually n sub j plus, okay, summation of f of I from I equals 1 to n sub j, okay, and it becomes this final equation, okay, and these are just equivalent, okay. This is equivalent to, this is the number of constraints, while n sub j is the number of joints with individual connectivity f sub I. Now for this, okay, for this joint, okay, it's actually okay, so we have n sub L, okay, n sub L equals 6 times, oh sorry, the degrees of freedom is equal to 6 times n sub L minus 1, okay, minus n sub C. Now, the constraints would be for every joint, correct? Okay, so you have here, okay, you have here 6, okay, 6 times 3. If you have the 4 bar linkage, okay, so it's 4, okay, 4 links minus 1 times number of constraints minus 5 minus 5 minus 5 minus 5. But that would result to, okay, minus 20. This is minus 2. Actually, it's because, okay, generally, okay, a 4-bar linkage with revolutes or pins in the joints, okay, that is actually an indeterminate structure, okay, if going to structures and buildings, okay. But, okay, for a certain mechanism as shown, okay, the crank rocker mechanism, the DOF is actually 1. And that is because you have 6 times 3. I'll just simplify that. Minus 5 minus, minus 5 minus 4 minus 3. And that results to 18 minus 17. And we have 1 degree of freedom. Okay. Okay. There are other joints. We have the prism, the helix, the cylinder, sphere, plane, universal, and the spur gear and the cam gears, cam gear pairs. Okay. Now, this types of joints already have their definite or defined symbols. You have also the schematic for this one. Okay, and then the schematic, for example, for the revolute is actually it's something like this. Okay, or something like this. Okay, that is a revolute. For the joint, okay, for the joint, okay, for the universal joint is actually something like this. Okay, right? Okay, that is the universal joint. Now, as the type of contact, okay, the universal joint is actually a lower pair, similar to the revolute, and it has 2 degrees of freedom in terms of the theta and the phi. Okay, and then there's also an example shown. Okay, as shown, the example is actually a hook type universal joint combining 2 revolute joints. Okay. Now the revolute is a pin joint. Okay, this is a pin joint. Okay, and it has 1 degree of freedom. Now at the other types of joints, okay, the prism, the helix, the cylinder, it's actually it's provided in a tabular format. Okay, it's available in very many literature and could be sourced easily. Now there are these are the joints, and a while ago, okay, there was the 4-bar linkage, and there are other types of linkages. Okay, we have here the crank rocker mechanism. You have the change point and the double crank. Now, if we want to see the movement of the crank rocker again, okay, as was shown, the position displacement analysis would lead to what? Something like this. Okay. Okay. At one point, okay, as the crank rotates, it leads the rocker on, but up to a certain limit, okay, in a maximum, and then there's another maximum to the other end, or the minimum. But the crank rotates at in 360 degrees. Okay, for the double crank, okay, it rotates both. Okay, both are cranks instead of one rocker. So the two links, okay, rotate in 360 degrees. There's also another one. This is change point. Okay, and it rotates both. Okay, but okay, take note that the 2 linkages are of the same length. Okay, and then there are other types of linkages like the 5-bar linkage. Okay, and there's also for example, the double rocker, or a triple rocker, and the 5-bar linkage. Okay, okay. There's also the slider crank mechanism. Okay, and this again have been defined in literature and could be sourced easily, but it's very important to tackle the analysis, okay, the position displacement analysis of this uh, linkages. And let's try to solve one, okay, given an example. And we have here a roller, okay, connected via two links to a pin joint, okay? And we know the roller is, it rolls along it has one translational axis, right? So it's rolling along the x-axis this way, okay? And we can predict the position of this one because, okay, this is determinable. We can actually determine the degrees of freedom, but that's not the point. But okay, so we proceed with the solution by determining, for example, a motion, okay, the motion or a specific position. Okay, for example, if this is what, if this becomes 60 degrees. Sorry, it's more than, I think, 60 degrees. So what we can do is we can move over to our graphical solution, okay? And what we do is we have here the simplified link mechanism between the pin joint and the roller. And what needs to be done is to identify the position at 75 degrees, okay? When this link, okay, moves to that position. Now, to do so, okay, we rotate this link, and this is a graphical solution. Rotate, okay. Or we can actually just copy this one first, okay. And so that we have a new one, okay, that we can compare to this other one, okay. Is it exact? Okay, we rotate this one 60 degrees to identify the position, okay. Negative 60. Okay. Oh, sorry. Is it 60? Yeah, negative 60. It should be 60, just 60. Apologies. You have to rotate this one. 60. All right, so that's the 60 degrees. Okay. Where is the sorry, I think I have to zoom this. All right, I think it's more than, okay. We can try, for example, 30 degrees, okay, 30 degrees. 30 degrees. Or maybe 15, 15, just 15. Okay, about this point, so just 15. Okay, so that's 15. Okay, so apologies, you have to copy. You have to copy so that we can compare the original position. Right, so that's a new position for this link, and you have to copy this one. Okay, to this end. But we know, okay, that this is only at the end. It's a roller that only has translational motion. So we have to align this one to this axis, okay. And what we can do is by making a circle, okay, so that we can connect this one So we can just create a new polyline. Okay, line that one, because we know that that is exactly just that. So the new position, okay, is actually removing the construction lines. Okay, the new position of the roller would be at this point. You can actually determine the dimension, okay, distance of that point to that, okay, and okay, graphically. Okay, all right. Okay, so that is how to do position analysis. And in the next discussion, it's going to be about uh, velocity and acceleration analysis. I'll be seeing you by then. Thank you for listening.